In our last two videos, we've talked about a couple of different concepts under this umbrella of integrals, right? Chapter 4 is all about integrals, and so we've talked about a couple different concepts related to integrals. 4.1, we talked about antiderivatives, which was finding functions f of x such that when you take the derivative of that function, you get the function you're looking for. Right? This idea of that's the opposite of derivative. What function will give me this as its derivative, okay? But then we also, in 4.2, we talked about area under the curve and how we can estimate that area by summing up a bunch of rectangles, okay? Summing up a bunch of rectangles that can estimate the area under the curve. Well, how are these, but then there was this way that these two things were related. They were related with this very skinny S symbol. In both of these sections, I used this skinny S symbol to represent an antiderivative or to represent an area under the curve. And so today we're going to learn why. Okay. Well, in our last video in 4.2, we talked about how if I use more rectangles, I can get a more accurate estimation, right? The more rectangles I have, the more accurate my estimation is going to be. Well, if I have a function, then what's stopping me from using an infinite number of rectangles, right? If more rectangles means more accurate, well, could I then pack in as an infinite number of rectangles that are all infinitesimally small, right? That are all have just an infinitesimal width? Couldn't I theoretically do that? Well, that's exactly where this symbol comes from. This symbol is an S because it represents a sum, but it represents a sum of infinitesimally small rectangles. It represents an infinite sum. So, in this case, dx represents my infinitely small width. If I have an infinite number of rectangles, each rectangle is going to be infinitely small. It will have an infinitely small width. Okay. And, of course, if I'm finding area under the curve, I have bounds. And those bounds represent where am I actually looking? Where am I starting? Where am I ending? Where am I actually calculating this area under the curve? Okay? So that's how this symbol connects to 4.2, but how does it connect to 4.1? Now, how does this connect to antiderivatives? Well, this leads us to, let me just rewrite that so it's a more convenient place. This leads us to what's called the fundamental theorem of calculus, which is what this section is called, the fundamental theorem of calculus. It turns out, as mathematicians worked more and more on this area under the curve and how to find it, they saw that it was very, very closely connected to antiderivatives. In fact, they found that you can use the antiderivative to actually calculate this area under the curve. It turns out that if you want to find the area under the curve over a specific interval, all you have to do is calculate the antiderivative, plug in your upper bound, and plug in your lower bound, and subtract the two results. Okay, so this right here is what's called the fundamental theorem of calculus because it simplified things so much. It all of a sudden made finding these infinite areas, right? These areas that involved a limit approaching infinity, it made it possible by just using the antiderivative. Okay? It's kind of similar to derivatives, where the whole concept of a derivative is you're getting infinitely close to something, but we found that you could actually calculate what it is, even though it's some value that involves infinity. Same thing here. This is a value that involves infinity because you're getting these infinitely small rectangles, and yet you can still calculate the value. So this is my fundamental theorem of calculus. So let's look at a few examples. Okay, let's take a look at an example. We have this function x squared minus 3, and we want to find the area under this function from -2 to 3. So if I were to write this out of what I'm actually asking for, I'm going to use this integral symbol because I'm finding the area under the curve, and I'm finding the area under the curve for this function. Dx is part of that integral notation. And since I'm going from -2 to 3, that means my integral has bounds. I have a lower bound of where I'm starting and an upper bound of where I'm ending. So if I have bounds, this means this is called a definite integral. Okay? So definite integral is where I have bounds. And x squared minus 3 is obviously a parabola because it's a quadratic function. So I have a parabola here, which means it's not linear. I can't find the area using geometry here. But this is what's so nice about the fundamental theorem of calculus. The fundamental theorem of calculus says I can find the exact area using antiderivatives. All I need to do is figure out what the antiderivative is. So what's my antiderivative for x squared minus 3? Well, my x squared term is going to give me x cubed over 3, right? 1/3 x cubed. And once again, if you're ever like, where does he get this from? Try taking the derivative, see what you get. If I take the derivative of x cubed over 3, I get 3x squared over 3, and the 3's cancel. Well, minus 3, what's the antiderivative of minus 3? I get just minus 3x, right? If you're taking the antiderivative of a constant, all you do is just put an x next to it. Okay? And then since this is an antiderivative, I really should have a plus c here. So there's my antiderivative, my family of antiderivatives for this function, but I'm evaluating this from -2 to 3. Okay? So you'll see this notation quite a bit as I go through this. This where I put the bounds there at the end. The other way you'll see it is I might just use a normal parentheses and then draw a line at the end like this. And this just means, this line means I still need to evaluate it from -2 to 3. What does that mean to evaluate it? Well, it just means this. I'm going to plug in the upper bound and plug in the lower bound and subtract the two different values that I get. Okay? So let's plug in the upper bound first. If I plug in the upper bound, I get 3 cubed over 3 minus 3 times 3 plus c. So there's the upper bound. And then I'm also going to plug in the lower bound. -2 cubed over 3 minus 3 times -2 plus c. And what am I going to do with these two values? I'm going to subtract them. Okay. Well, with my upper bound, I get -3 cubed is 27. 27 over 3 is 9. Minus 3 times 3 is 9 plus c. So the 9's are going to subtract equal 0, and I'm just going to be left with c on this left side. But on the right side, I'm left with, let's see, -2 cubed is -8. -8 over 3 minus 3, but then I'm going to multiply that by -2, so that gives me a +6 plus c. Okay, so what am I left with? I'm left with c minus a -8/3 gives me a +8/3 minus 6 minus c. What happens to the c's? The c's are going to cancel equal 0. And I'm left with, let's see, 6. If I write that in terms of thirds, I get 18/3. So I get 8/3 minus 18/3, and I get -10/3. That's it. No c. Now, I want to say this before we talk about this answer. Notice how the constants ended up canceling out. Okay, because your constant is going to be the same for the upper bound and the lower bound, and because the fundamental theorem of calculus involves subtracting those two values, your constants will always cancel out. So with definite integrals, so as long as you have bounds, you don't need to worry about plus c. You don't need to tack on a plus c because those c's are going to cancel out during your calculations anyway. So with definite integrals, you don't need to worry about adding a plus c. But now let's think about this answer. My answer is negative. What does a negative area mean? How am I getting a negative value for my area? What's going on here? Well, let's draw a picture to help me make sense of this. If I draw a picture of my function, remember my function is x squared minus 3. What that gives me is a parabola, but a parabola that goes under the x-axis and has a vertex there at -3. And then I'm integrating from -2, which is about here, to +3, which is about here. That means I'm finding the area under this graph from there to there. Well, if you remember in the last video, when I say area under the curve, what am I actually talking about? I'm not saying area under the curve all the way down to -infinity, because otherwise all of my areas are going to be infinite. I'm just talking about the area under the curve all the way down to the x-axis. So that's easy enough to understand when I'm looking at these positive sections, right? But how do I work that if my function goes underneath the x-axis, right? I don't want to suddenly start doing area under this curve, because once again, I get an infinite area. Instead, the area under the curve really means the area between the curve and the x-axis. So if my function ever goes negative, then now you're calculating the area between the curve and the x-axis. So, back to my original question, why did my answer end up outputting as a negative area? Well, that's because the area underneath the x-axis ended up being larger than the area above the x-axis. And we count area under the x-axis as negative. Okay, so that's an important thing to remember. Okay, so to summarize here, to go over some kind of big ideas before we move on to the next example. When I use a definite integral, I'm talking about the area under a curve. Okay, or right, like I just talked about, when I say area under the curve, I'm actually talking about the area between the graph and the x-axis. Okay, between the graph and the x-axis. So whenever you see bounds, we're talking about a definite integral, and I want you to find the area underneath the curve. So what if you don't see bounds? What if I gave you this equation without bounds? X cubed, or x squared. What if I gave you this integral without bounds? What would I be asking for then? Well, if I don't give you bounds, where are you actually finding the area? Right? Does this mean you're finding the area over the whole domain? Well, it turns out we have something else for that. If I don't give you bounds, that means I'm not actually asking for an area. If I don't give you bounds, all I'm asking for, we call this, let me go and say this. We call this an indefinite integral. Okay, so we have definite integrals and indefinite integrals. Indefinite integrals is if you don't have bounds. And all I'm asking for with the indefinite integral is, what's the antiderivative? This goes back to 4.1, right? 4.1, I used this notation And this is why. An indefinite integral, all I'm asking for is the antiderivative. And in this case, because I'm just looking for the antiderivative, do I need the plus c? Absolutely. Okay. You need the plus c. Because that's an important piece of what the antiderivative is. The antiderivative could have any constant added on here. So to finish off this section, I wanted to look through a couple of related examples, both talking about a particle moving, right? The movement of a particle. And I wanted to highlight these two different examples because they're both asking fundamentally different things. So let's look at example one. So for the example one, we're given the acceleration function for the particle. What does the acceleration of the particle look like? Well, I'm given the function. The acceleration after a certain amount of time is negative 18t plus 6. And then it also gives me these little pieces. V of 0 equals 6 and S of 0 equals 10. And then it wants me to find what is the position function. Okay. Well, what do we know about acceleration? How is acceleration related to position? Well, if you remember, the derivative of position is velocity, and the derivative of velocity is acceleration. So the second derivative of position is the derivative of velocity, which is acceleration. Okay, that means I want to go this direction. So what am I actually doing here? Well, it's 4.3. Now that we know what this symbol actually means, all I'm really trying to figure out is, am I finding a definite integral or am I just finding an indefinite integral? What do you think? For example 1, since we're finding a function, we're just finding the indefinite integral here. We're just finding what the antiderivative is. The tricky part about it is that we have to do it twice. If I want position, I have to find the antiderivative twice. So all I'm doing here is finding an antiderivative. So this example 1, is an indefinite integral. I'm taking the indefinite integral of negative 18t plus 6. dt now because my variable is in terms of t. Okay. And let's see what happens. So remember, this is acceleration. So if I take the indefinite integral, which means all I'm doing is I'm finding the antiderivative, I get negative 9t squared, because that's negative 18 over 2, right? Negative 18t squared over 2, so I get negative 9t squared plus 6t plus c. What does this equation represent? Since it's the antiderivative of acceleration, this is my velocity function. This is my velocity function. Everybody okay with that? So, but you'll notice I have a plus c in there, right? Because this represents I could have an arbitrary constant. Well, take a look back at the information they give us. They give me this value, v of 0 equals 6. That's related to my velocity function. What does that actually mean? This represents my initial velocity, because it's the velocity at time 0. If I plug in 0 into my velocity function, I should get 6. So let's do that. What happens when I plug in 0? V of 0 gives me negative 9 times 0 squared plus 6 times 0. Both of those terms are just going to go to 0, and I'm left with c. And according to my initial condition, this needs to equal 6. So that leaves me with this velocity function. Negative 9t squared plus 6t plus 6. Now, if only I were done here. But remember, I'm trying to find the position function, which means, what do I do with this velocity function? I take the indefinite integral of it again. Right? I've gone this far, right? Here's a little, I'll put a star here because this is like those maps. You are here, right? I've gone this far. I've taken the antiderivative once to get my velocity function. I now need to take the antiderivative again to get my position function. So what does that give me? Okay, this gives me, I'll slow it down in this one. So I add 1 to the exponent and divide by that number. Same thing here. I get 6t squared divided by 2. And then with my second 6, once again, all I'm doing is I'm just adding a t onto that constant, and then I get another constant. When I take this antiderivative, I get a new arbitrary constant for this second antiderivative. Okay. And this, if I simplify this a little bit, negative 9 over 3 is just negative 3t cubed, plus 6 over 2 is just 3t squared, plus 6t, plus c. This represents my position function. But, once again, since this is a family of antiderivatives, this could be an infinite number of position functions. How do I know it matches my specific particle? Well, that's where this comes in. S of 0 equals 10 is my initial position. So I can plug 0 into this position function and see what I get out and make sure that that's going to be 10. Well, the same thing's going to happen. All I'm going to be left with is C again. So all I need to do is just say, okay, C is going to equal 10. Because my initial position is 10. So that leaves me with the following function, negative 3t cubed plus 3t squared plus 6t plus 10. And that would be my final answer. Okay. So sure enough, example 1 just ended up being an indefinite integral, where all I was doing was I was just finding antiderivatives. I just had to do it twice. What about example 2? Is example 2 going to be the same thing? So here in example 2, I'm given a velocity function, and I'm asked two very specific questions. How far, if this is the velocity of a particle in feet per second, how far has the particle traveled in the first 5 seconds? And then B is similar. How far will it travel during the next 5 seconds? Well, what are your thoughts? Definite integral or indefinite integral? In this case, this is a definite integral. And how do I know? The only difference between the two types of integrals is whether or not you have bounds. Do I have bounds for part A? I absolutely do. Remember, your bounds are x values, or in our case, t values, since t is my independent variable. So what would my t values be? If I'm looking at the first 5 seconds, I'm going from 0 to 5. What about part B? What are the next 5 seconds? 5 to 10. So in both of these cases, I have bounds. I have specific t values that I'm going to start at and a t value that I'm going to end at. So that makes this a definite integral. Well, why is it a definite integral? Well, I mentioned this back in the 4.2 video. If you have a rate of change function, then the area under the curve represents the total change. The area under the curve represents the total change. So in our case, the total distance that the particle has traveled, because velocity is a rate of change of position or distance. So for part A, I'm finding the integral from 0 to 5 of negative 0.5 t squared plus 6t. Well, according to my fundamental theorem of calculus, all I have to do is find the antiderivative. And since this is a definite integral with bounds, I don't need to stress about the point plus c. So what do I get? I get negative 0.5 t cubed over 3. Well, negative 0.5 over 3 is actually just 1 over 6. So I get negative 1 over 6 t cubed plus 6t, and then I'm going to have t squared over 2, so that just gives me 3t squared. And then I'm going to evaluate that in fact, I'm not going to worry about the bracket. I'm going to evaluate that from 0 to 5. Okay? When I plug in 5, I'm going to get, I think I get like negative 125 over 6 plus 75 minus, what happens when I plug in 0? I get 0 plus 0. I just get 0. Okay? Once again, because I don't have to stress about the arbitrary constant. Okay, that simplifies to about 54.16, and I'll round 167 feet. It's traveled 54.167 feet. Okay. For the next 5 seconds, I'm doing the exact same thing, except I'm just going to change the bounds a little bit. Now I'm going from 5 to 10. And what's nice is I've actually already found the antiderivative. The antiderivative, since I didn't change the function, the antiderivative is exactly the same, but now I'm evaluating it from 5 to 10. Okay? If I plug in 10, I get negative 1,000 over 6 plus 300. Minus, if I plug in 5, well, I already did that math. That's negative 125 over 6 plus 75. When I plug all that into my calculator, I get 79.167. Okay. So I wanted to go through both of those examples because it's a great way to look at, okay, is this an indefinite integral or is it a definite integral? Your key difference is, does it give you bounds? If it gives you bounds, you're doing a definite integral, like example 2. Okay, good luck on the homework. There are a few problems that you might look at and think, this is so tricky, but the key with most of these is just being able to rewrite your function. If you can rewrite it as a power function, you're good to go. But please reach out if you have any questions, and we'll talk to you in the next video.